Hello everyone, welcome to the session 3 of module 4. So till now we have covered the major topics till here, and we are left with the allocation of the frames and the thrashing. We shall discuss one by one now. During the discussion of allocation of frames, the first question that arises is how do we allocate the fixed amount of a free memory among the various processes? So this is the first question that we face. So before getting into in detail, let us take a simple example here. So you have a case in which there is only single user systems are there, single user system. So in this single user system, let us consider a memory which is of size 128 KB. So this memory, which is composed of pages, each page is of size 1 KB. So the system has you can consider as 128 frames. So we need some pages that required for an operating system for its smooth executions and also other IO operations. So for that we allocate 35 KB, that is 35 frames for an operating system, and remaining is we get 93 frames for the user process. So under the concept called as a pure demand paging, see, all these 93 frames would be initially taken from or would be kept in a free frame list. Okay, so when these 93 frames are kept in free frame list, whenever a user process starts its execution, so it generates a sequence of page faults. So you know that the pages which are required for a smooth execution, those pages are not available in the main memory. So the pages has to be loaded from the secondary to the primary. So this is the concept. So all these 93 frames are utilized initially. Means these pages or 93 page faults would get all free frames from your free frame list. So when this 93 frames list was exhausted, means when these all are taken for its execution, now a page replacement algorithm would select one of the page from this 93 in memory page that need to be replaced with the next consecutive page. That is, assume that we need to replace with the 94th or 95th pages, so and so on. So this concept is very simple. The 93 pages are utilized for process. Whenever I want to take 94th page for the execution, it has to replace any one of the frame from this one. So this is the basic concept. So when the process terminated, means after the execution of the process, when the process terminated, all the 93 frames which are allocated to that process would be taken back, and this is given to the or placed on the free frame list. So this is the simple use case scenario. So there are many variations on this simple strategy. Okay, that is, the operating system may require some of pages from the free frame list for its buffer and also for table space. Okay, when this space is not used by the operating system, that can be used for, or that can be used for supporting the paging purpose. So we also need to keep additional frames. Assume that we shall take 3 frames which is reserved for a free frame list at all the time. Okay, whenever the page fault occurs, these frames which are available as a free pages that can be used for page replacements. So this is another variation of this simple strategy. The next concept is with respect to the minimum number of frames. Remember, one of the strategy for allocating of a frames has different constraints on these methods, means the different restrictions on this, because we cannot allocate more than the total number of available frames to the process. So we must allocate at least a minimum number of frames, because there are so many reasons, and one of the major reason is, see, if we allocate at least a minimum number of frames involves in terms of performance. So you know that as the number of frames allocated to the each process which decreases, the page fault rate will also increases. So this consequences in the slowing process execution. This is one thing. Second one, you should remember this one, that is, whenever a page fault occurred before an executing an instruction that is not completed, that instructions again it has to be restarted. So whenever you allocate frames to the process, you should have enough frame to hold all the different pages that a single instruction can reference. Remember one thing, the minimum number of frames per process, that is defined by the architecture of your systems. Second one is the maximum number is defined by the amount of available physical memory. So these are the basic information with respect to the minimum number of frames. See, there are simple algorithms which are used to allocate the frames. One is the fixed allocation, priority allocation, global versus local allocation. The first one is fixed allocation. So in the fixed allocation, we shall consider the first step is the equal allocation. Means this is one of the easiest way to split a frame in among the n process, so that each process will get an equal share. So we shall take an example here. So if there are 93 frames are there, I want to allocate these 93 frames among the 5 process. So if it is so, each process will get 18 frames, and there are 3 frames which are left over that can be used as free frame buffer pool. So this scheme is called as equal allocation. So the previous strategy, that is equal allocation, it has some limitations, or we can call it as a disadvantage, because assume that you have a system which is having a free frames of size 62. Assume that you have two processes P1 and P2. These are the two processes which are currently running in your system. So P1 need only 10 KB of memory and P2 need 127 KB. So if I go with an equal proportion, so I would get 31 and 31 free frames, that is 31 for P1 and 32 for P2 free frames for execution. So you can see here the process P1 need only 10 KB, but I have allotted 31 KB. So here 21 KB of memory is wasted here. So to solve this problem, we have another strategy or another method called as proportional allocation, which means that we are going to allocate the memory which is available to each and every process based upon its size. Let us consider some of the terminologies here. One is SI, which we call it as size of the process PI. So capital S is called as, that is summation of S small I, means a total number of process sizes. Okay, so assume that you have a process P1 which is having 10, P2 which is having 127, and P3 which is required is 50. So total is summing of all these 10 plus 127 plus 15. So this is the value of capital S, and M is the total number of frames which are available in my system. So if I want to allocate the frames to an individual process, so this is the formula. So Pi is equals to Si by S multiplied by M. So let us consider a simple example here. The example is the size of M is 62. That is the total number of available frames, which is denoted as M. The size, that is 62. We need to allocate, that is AI frames, to the process Pi. So how do you approximate that value AI using this formula? So S1 is 10, that is the frame which is required for process P1, the size S1, and S2 is 127. So the total is 137. So in order to identify the values, formula will be 10 divided by 137 into 62. So approximately you will get 4, and for A2 the value is 57. So in this way, the both process shares the available frames according to their needs rather than equally. So the next algorithm is a priority allocation. See, we have seen in the previous allocation, that is either in the equal or proportional allocation, the higher priority process and the lower priority process, both the processes are treated equal, means both the processes are same. So but we want a higher process or higher priority process need to be executed at a faster pace than your lower priority process. So in order to go with that, we need more memory for higher priority process. So one of the solution is to use a proportional allocation scheme, wherein the ratio of the frames depend not on the size of the process but on the priorities of the process, or on combination of these size and the priority. So assume that you have a process, that is Pi, which generates a page fault. So how do you do that? So when the page fault occurs, you need to replace a page by selecting any one of its frame which is available or which need to be taken from the main memory. So selecting a page or selecting a frames that need to be replaced, you need to select a frame from a process which is lower priority than the other process. So this is the way to select the frames with respect to the priority allocation. The next topic is global versus local allocation. As you know that the frames are allocated to the various processes with respect by using your page replacement algorithms and methods. So when the multiple processes are competing for the frames, these page replacements algorithm can be categorized into two categories. One is global replacement and another is local replacement. So what is a global replacement? So global replacement that allows a process to select a replacement frame from the set of all the frames which are available in your system, that is available in your main memory. Even that frames which are currently allocated to the other process, that frame can also be used for the process which is in need. So which means that one process can take a frame from the another process. So this is with respect to the global replacement. But whereas in the local replacement, the frames that are required for a process, that process need to select only from its own set of allocated frames. So this is with respect to local replacement method. But there are some advantages and limitations are there. When you go with the global replacement, the process execution time may vary at the greater extent, but you will have a greater throughput. But whereas in the local replacement, there is more consistent with the process performance. That is, individual process performance, there will be consistency. But whereas in the global replacement, this is not correct with respect to global replacement, because the frames which are allocated to the other frame, that frames can also be taken back and give it to the process. Means the performance of the systems may vary because the allotted frames are taken and given to the other frames. So even that frame performance increases, but here the other process performance will decrease. So there is no consistency between the performance of individual process. But whereas in the local replacement, there may be a chances of underutilized memory. So the next topic is non-uniform memory access. So till now, whatever the topics we have covered, we have assumed that all the main memory is created equal, and at least those memory has been accessed equally. Okay, so on many computers, that whatever we have, this is not the case. Means the memory is not accessed equally. So there are systems with the multiple CPUs where some of the CPUs can access some section of main memory faster than the other CPUs. So this causes a performance difference between the CPUs. So the performance of this CPU is caused by how the CPUs and the memory are interconnected in the system. So some of the systems which are made up of several boards, where each board contains multiple CPUs and some of the memories. So these system boards are interconnected in different ways. That might be using some system buses to high-speed network connections. So these CPUs which are connected on a particular board can access the memory with the less delay than the other CPUs on the other boards in a system. So systems in which memory can access or memory access time vary significantly, which is known as non-uniform memory access system, and without exceptions they are slower than the system in which memory and CPU are located on the same motherboard. See, managing which frame are stored at which location, that can significantly affect the performance of affect the performance in non-uniform memory access systems. So remember, if we treat the memory as uniform in nature, the CPUs may have to wait significantly longer time for accessing the memory than if we modify some of the memory allocation algorithm such that those algorithm can take this non-uniform memory access into account. Remember, similar changes has to be made to the scheduling system. So here, during the changing of scheduling system, there should be a goal such that whatever the changes is done, that these changes has to be reflected to memory frames. Those are allocated as close as possible to the CPU on which the process is running. So here the close, which means that with the minimum latency, which is typically means on the same system board as the CPU. So this is with respect to the non-uniform memory access. So the next topic is thrashing. So we know that whenever the pages which are required for execution, if those pages are not available in your main memory, those pages has to bring from the secondary to the main memory for its execution. Similarly, we have some of the pages, those pages are considered as active pages, means for some time duration these pages are required for execution by the CPU. So assume that process P1 which needs some pages, so the frame size is 3. Assume that I have 2, 3 and 4 pages. So if fifth page comes into the picture, what I need to do, I have to replace any one of the pages, any one of the page for the execution. Assume that I have replaced page number 2, so with the fifth, so 5, 3 and 4. Again, see, as soon as I replace that, again if the CPU wants, the second page, so again what I do, I replace 2, 3, 4. Again if the CPU wants the page number 5, so 5, 3, 4. So here the pages which are replaced, which are needed in the further use, or what we call it as, these pages are in active state. So here the CPU is busy in just performing a page replacement rather than execution of the process. So the maximum time which is spent on just swapping pages in and out. So this process or this high paging activity is called as thrashing. So a process is thrashing if it is spending more time in paging than executing. So which lead us to low CPU utilization, and operating system, remember here, the operating system thinks that because of the low CPU utilization, operating system thinks it has to bring, or it needs to increase the degree of multi-programming, which means your operating system thinks the CPU is underutilized, so I have to bring the other process to the CPU so that it will increase the degree of multi-programming. So the next is the cause of thrashing. Here, because of thrashing, there are some of the performance issues are there. We know that operating system monitors the CPU utilization. If the CPU utilization is low, then what operating system does? It will bring some other new process to the system so that it can increase its CPU utilization. As soon as the new process bring for execution, if the pages are available in the main memory, there is no issues. If the pages are not available, then page fault occurs. So it has to replace the frames to this new process. What it does, the process will take the frames which is allotted to the other process. When it is allotted, means when the process is taken frames from the other process, the process CPU utilization decreases. Again, the page fault rate increases. What your operating system thinks now, again, the CPU utilization is low, so bring the new process. So this process keep on increasing, so which leads to the lower CPU utilization and high page fault rate. So here you can see in this diagram, for some extent you can see as you increases the multi-programming with respect to the CPU utilization will also increases till this extent, you can see here till here, as you increases the number of process, CPU utilization is also increased. At certain point, you can see even if you increase the degree of multi-programming, the CPU utilization means the CPU is not utilized properly, and this rate keeps on decreasing, which means the thrashing has introduced now. So what is the one option here to stop your thrashing? We have to decrease the degree of multi-programming, and another is we can use a local replacement algorithm so that the process will not take the frames which is allotted to the other frames, but this, by using this method, the entire problem might not solve. So there are some of the ways where we can solve or we can avoid the thrashing. One is working set model and another is page fault free. So how do we prevent the thrashing? So we have to know that how many frames which are required to a process for its execution. So to know that how many frames are required, there are several techniques are there. One is the working set strategy. See, this working set strategy mainly depends upon the locality model of a process execution. So what actually the locality means? Assume that your process or a program consists of a set of instructions and also multiple functions. Assume that this is your function 1, and this function may consist of several set of instructions. So when the process execute its execution, when the process starts its execution, the control may be given to this function for its execution. So this function may be executed for multiple times. Assume that this function is called for 10 times, and these instructions are active in nature for certain period of time. Okay, and these references which are made for these instructions, like memory references which are made to these instructions of a function call, and its local variables and some set of global variables. So these references which are used for a certain period of time, and these references are active in nature, and this is called as a locality. This is one locality. So your process or your program may contain multiple functions, or we call it as multiple localities. So when this functions completes its execution, your process may leave this locality and it may start executing with the other locality, and the process may come to this locality at the later stage, because the instructions which are not needed right now. So this is with respect to the locality. See, as a program continues its execution, it may jump or it may move from one locality to other locality, because your program may composed of several different localities which may be overlapped also. When we thrashing occurs when the size of the localities, as I said, that locality is your program may consist of multiple localities. If the size of all localities increases the total memory what we have, then it causes a thrashing. See, as we have already seen that this working set model is mainly based on assumption of locality. So here in this model we use one parameter to define the working set window. So what actually this working set window is? This window consists of pages which are recently used, or which are pages which are referred recently, and this set is called as working set. See, if a page is in active use, then it will be in the working set. If the page is not used, then it or that pages will be dropped from this working set window. In this diagram, you can see here there is a sequence of memory references which are made here. Assume that if the delta, that is working set window, is 10 memory reference, then working set time t1 is from here to here. That is, you can see page number 1, 2, 5, 6, 7. So these are the pages which are in your working set window. Here the delta is set as 10. You can see here, you can count here, there are 10 page references are there from 2 to 1. So in this time slot T1, how many pages are active in nature? You can see page number 1, 2, 5, 6 and 7. Similarly, there is another time that is defined by T2 and the delta, that is working set window, which is start from here, time reference till here. If I want to know which are the pages which are active in this given time, the working set window consists of 2 pages, that is 3 and 4. So this is with respect to the working set. The most important thing is the accuracy of this working set depends upon the selection of this working set window of that particular process. So if this working set window is too small, if it is too small, it cannot accommodate even a single entire locality. So that causes page faults, and it increases page faults. As if the page faults increases, you know that the thrashing will also comes into the picture. If this working set window is too large, it may overlap many localities. If this window is infinite, it can accommodate the entire program in the set of working set of windows. See, the most important property of this working set is depends upon the size. If we are able to compute what is the working set size, that is WSS of that particular process, then maximum problem will be solved. Here you can see the formula D is equals to summation of WSSI. It means D is the total demand of frames for each and every process which are actively using the pages in its working set. So if this total demand is greater, means if the D is greater than the total number of frames which are available, then thrashing will occur. So the important thing is we have to select a working set window. That selection, the size of selection of this working set window plays an important role to avoid the thrashing. See, once this working set window has been selected, the use of working set model is very simple. The thing is, see, your operating system will monitor the working set of each and every process and allocates to that working set enough number of frames to provide with respect to working set size. If there are enough extra frames, other process can be initiated. If the sum of the working set increases, which also exceeding the total number of available process, the operating system select the process to suspend. See, we have seen in the working set strategy, whenever the page fault rate increases, we have suspended a process, and whatever the frames which are allocated to that process that are made free, and that frames are allocated to the process which are in need, means which with the process which are having high page fault rates. This is with respect to working set strategy. But there is another approach that is called as a page fault frequency, and this is direct approach that can be used to prevent thrashing. As we know that thrashing has a high fault or high page fault rate. So we want to control this page fault rate. In this diagram, you can see that there are two major bounds are there. One is upper bound and lower bound, and also you can see the axis. This axis is with respect to the total number of frames which are allotted to the process, and this is the page fault rate. If the process having higher page fault rate than your upper bound, which makes sense that, or which tells that these process need more number of frames, so we have to increase the frame size, or we have to allocate more number of frames to these process. Similarly, if the process page fault falls below this lower bound, then we have to decrease the number of frames which is allotted to this process. So this is a direct measure, and we can control the page fault rate to prevent your thrashing. So this is with respect to page fault frequency. So this completes the third session. Thank you so much.